In the previous classes, we learned to obtain interpolating polynomials using forward differences and backward differences in the case when the information about the function is given at a set of nodal points which are equally spaced. Then we learned to construct an interpolation polynomial known as Lagrange interpolation polynomial for the case when the information about the function is specified at a set of points xi which may be arbitrarily located. So, now in this lecture we shall see how we can obtain an interpolating polynomial using divided differences. So, this requires definition of divided differences of various orders. So, we first introduce the divided differences. So, let f of x y equal to f of x be known at say points xi for I is equal to 0, 1, 2, 3 up to n. Xi's need not be equally spaced. And let f of xi for I is equal to 0, 1, 2, 3 up to n be the corresponding values. So, we define divided differences of orders 0, 1, 2, 3 etc. as follows. So, I denote by the 0th order divided difference as f of x naught, and that is nothing but the value of the function at x naught. And then this is a divided difference of order 0. And then I introduce a divided difference of order 1 and denote it by f of x naught x1, which is f of x1 minus f of x naught divided by x1 minus x naught. The notation is f of x naught x1 is f at x1 minus f at x naught by x1 minus x naught. But you know that f of x1 is the 0th order divided difference at x1 minus 0th order divided difference at x naught by x1 minus x naught. So, the first order difference divided difference can be given in terms of the 0th order divided differences. So, this is the definition for the divided difference of order 1. So, we write down now the divided difference of order 2 and denote it by f of x naught x1 x2. So, that will be f of x1 x2 minus f of x naught x1 divided by x2 minus x naught. And we have just now constructed the divided difference of order 1. So, we use that definition here, and divided difference of order 1 we again use the definition and then write down what the divided difference of order 2 is. So, this is divided difference of order 2. So, we continue this way and write down this divided difference of order n as f of x1 x2 etc. xn minus f of x naught, x1, etc. up to xn minus 1 divided by, it is going to be now xn minus x naught. So, this is divided difference of order n. So, it is possible using this definition to construct the divided difference table, and from there we will be able to write down the interpolating polynomial using the information from this table. So, we are given information about x and f of x at a set of points, say x naught, x1, x2, x3, and the corresponding values are f of x naught, f of x1, f of x2, f of x3. So, I would like to form the divided difference table for the given information. So, I write down the column in which I am going to get the divided differences order 1. So, by definition we know this is the divided difference of order 0, this is the divided difference of order 0, and so on. So, I require the entries in divided difference of order 1. So, I know it is f of x1 minus f of x naught by x1 minus x naught, and the notation is f of x naught x1, and by definition it is f of x1 minus f of x naught divided by x1 minus x naught. So, I write this entry between these two entries and denote it as f of x naught x1. So, if I use the information here, the next entry must be f of x1 x2, and I know the definition is f of x2 minus f of x1 by x2 minus x1, and then the entry between these two will give me the divided difference of order 1, and that is f of x2 x3. So, having got the divided differences of order 1 from this table, we move on to the divided differences of order 2. So, again if you look at the definition, it is f of x1 x2 minus f of x naught x1 by x2 minus x naught. So, I have these two entries here. So, right in the middle, right, f of x1 x2 minus f of x naught x1 divided by, remember it should be now x2 minus x naught, and this is what you denote by f of x naught x1 x2. So, similarly you have these two entries, and so you will get the second order divided difference, which is f of x1 x2 x3. What is it? It is f of x2 x3 minus f of x1 x2 divided by x3 minus x1. So, this will be f of x2 x3 minus f of x1 x2 divided by, you have used information at points x1 x2 x3. So, it is divided by x3 minus x1. So, you have constructed the column in which divided differences of order 2 have been obtained. So, let us now work out the column in which we have divided differences of order 3. So, we have divided differences of order 2, and hence if we find f of x1 x2 x3 minus f of x naught x1 x2 and divide. So, this minus this will give you, so what is it that we have to write down? x3 minus x naught, and that is going to be f of x naught x1 x2 and x3. So, this gives you the divided difference of order 3, and this is constant. So, the higher order divided differences beyond the third order divided difference will all be 0 for the information given in this table. and the third order divided difference is constant. So, given some information about f at discrete points, we use the definition of divided differences and have formed the divided difference table. So, with this information, we should see now whether we can construct an interpolating polynomial that interpolates a function f of x at a set of discrete points xi, where the xi's need not be equally spaced. So, let us assume that we are given information at n plus 1 points. So, let y equal to f of x be known at xi for I is equal to 0, 1, 2, 3 up to n. The corresponding values of f of x are f of xi at I is equal to 0, 1, 2, 3 up to n. So, I want to reconstruct this function f of x. So, I seek a polynomial Pn of x of degree at most n that interpolates this function f of x such that, so seek Pn of x such that Pn at xi is f of xi for I is equal to 0, 1, 2, 3 up to n. So, in order to do that, let us write down the polynomial Pn of x in this form. Namely, let it be a naught plus a1 into x minus x naught plus a2 into x minus x naught into x minus x1, a3 into x minus x naught, x minus x1 into x minus x2 plus etc. Now, you know the pattern in which every term is added to this polynomial. So, I see that the first term is a constant, the second term is a linear polynomial, the third term is a second degree polynomial, the fourth term is a third degree polynomial, and so the n plus 1th term will be a n into an nth degree polynomial x minus x naught etc. up to x minus x n. So, when it is the second term, the coefficient is 1, first term coefficient is a suffix 0, third term coefficient is a suffix 2 and so on. So, this is the n plus 1th term, so the coefficient is a suffix n. So, we seek a polynomial in this form. So, let Pn of x be this. So, what do we want? We want Pn to satisfy condition Pn of xi is f of xi. So, let us find out what this condition yields. So, what is Pn of x naught? It is simply a naught, because all these terms have x minus x naught as a factor in them. So, what is a naught? Pn of x naught must be f of x naught. So, a naught is obtained. But what is this? This is the 0th order divided difference f of x naught. So, we now apply the next condition. Pn at x1 is going to be a naught plus a1 into x1 minus x naught, right, a naught. But what is Pn at x1? It is f at x1. So, this tells you that f at x1 is equal to a naught, which is f of x naught, plus a1 into x1 minus x naught. Therefore, a1 can be written as f of x1 minus f of x naught by x1 minus x naught. But that is nothing but the 0th order difference f of x1 minus 0th order difference f of x naught by x1 minus x naught, and this is by definition the first order difference f of x naught x1. So, we saw that a naught is the 0th order difference of f of x naught, a1 is the first order difference f of x naught x1. Let us work out the coefficient a2 and then we can generalize and write down what an is in this polynomial. So, let us find out what a2 is. So, I satisfy the condition Pn at x2 must be equal to f of x2. So, Pn at x2 is f of x2 and that is equal to, so we use that there, a naught plus a1 into x2 minus x naught plus a2 into x2 minus x naught into x2 minus x1. So, we substitute for a naught. A naught is f of x naught plus a1, we have already obtained a1 and what is it? That is f of x naught x1 multiplied by x2 minus x naught. We do not know what a2 is and we are trying to determine a2 using this condition. So, from here we obtain a2 as f of x2 minus f of x naught. So, this minus f of x naught x1 multiplied by x2 minus x naught divided by x2 minus x naught into x2 minus x1. So, a2 is given by this expression and we expect from the pattern of the coefficients that we have got, since a naught is the 0th order divided difference, a1 is the first order divided difference, we expect that this should give us the second order divided difference. So, let us do some manipulation on the terms that appear here and try to see whether what we think is going to be correct. So, we rewrite this term as follows. This is f of x2 minus f of f of x2 minus f of x1 plus f of x1 minus f of x naught. So, I have subtracted f of x1 and added f of x1. Then minus, what I do is, I shall take this part, I divide by x1 minus x naught and multiplied by x1 minus x naught. So, I have not done anything except that I have added the term f of x1. The other terms remain as they are. So, then I have minus f of x naught x1 multiplied by x2 minus x naught, that is this term. The whole thing is divided by x2 minus x naught into x2 minus x1. So, let us try to see what this gives us. So, a2 will be equal to the first two terms, let us write them as they are, f of x2 minus f of x1. Let us look at the next term. It is f of x1 minus f of x naught by x1 minus x naught. Just see this, which can be expressed in terms of 0th order divided difference and yields the first order divided difference f of x naught x1. So, this term is the first order divided difference f of x naught x1. So, we write down that term as plus f of first order difference x naught x1, but that is multiplied by x1 minus x naught. So, that into x1 minus x naught. Then I have the next term which also has the first order difference f of x naught x1 and that is multiplied by x2 minus x naught with a negative sign. So, I shall take this term. So, this will be minus x2 minus x naught. So, we have taken into account the numerator, the denominator is whole thing by x2 minus x naught into x2 minus x1. So, we write this as f of x2 minus f of x1 by x2 minus x1 by x2 minus x0. So, I take these two terms by the denominator and put it in this way. So, I am left with plus f of x0 x1 into, so I have a minus x0 plus x0 and I am left with x1 minus x2. So, I shall write that as minus x2 minus x1. I have x1 minus x2, I rewrite that as minus x2 minus x1 by the denominator x2 minus x0 into x2 minus x1. So, cancelling, they are distinct numbers. So, I am left with this. So, can you tell me what this is? This is the zeroth order divided difference at x2, zeroth order divided difference at x1 by x2 minus x1, and therefore, this must be the first order divided difference f of x1 x2. And what do we have here? It is the first order divided difference x0 x1, and both the terms are divided by x2 minus x0. So, recall the definition of the second order divided difference. It is f of x1 x2 minus f of x0 x1 by x2 minus x0, and we denote this by f of x0 x1 x2, which is the second order divided difference. So, we expected that A2 will give us the second order divided difference by looking at A0 and A1, and we show that yes, it is so. So, following in the same way, we can show that A3 will be the third order divided difference x0 x1 x2 x3, and if I continue this way, one can show that An is the nth order divided difference x0 x1 x2 etc. xn. So, which means that all the constants which appear in our polynomial Pn of x have been computed in terms of the various order divided differences. So, we substitute. So, we obtain therefore the interpolating polynomial Pn of x of degree at most n that interpolates the function f of x at a set of discrete points xi for I is equal to 0 to n, and it is given by A0, which is f of x0, plus A1, which is f of x0 comma x1 multiplied by x minus x0, plus A2, which is f of x0 x1 x2 multiplied by x minus x0 into x minus x1 plus etc. So, I write down f of An, which is f of x0 x1 etc. xn into the factors will be x minus x0, x minus x1 etc. up to x minus x n minus 1. So, here, so this is x n minus 1. If it is A3, we stop with 2, it is a polynomial of degree 3. When it is An, then we have a polynomial of degree n. It starts at x0, so it goes up to x n minus 1. So, there are n such factors. So, the degree of this polynomial will be n. So, we have constructed a polynomial Pn of x of degree at most n with the property that Pn at xi will be equal to f of xi for I is equal to 0, 1, 2, 3 up to n, and this polynomial is called the divided difference interpolating polynomial. Divided difference interpolating polynomial. The greatest advantage of divided difference method is the following. If suppose I have another information about this function f of x, right, about this function f of x. Say at the point xn plus 1, and the information is f of xn plus 1. It is just not at one point. Whatever be the number of points at which you get extra information about the function, the following can be done. We just explain this in case we have one additional information. If we have one additional information, then we have totally a set of n plus 2 points at which the information is available. And therefore, we want to reconstruct this function whose values are known at a set of n plus 2 discrete points. And therefore, we can seek a polynomial of degree n plus 1 that interpolates this function at a set of these n plus 2 points. Already we have constructed a polynomial that interpolates the same function at a set of n plus 1 points, and this has been obtained using divided differences. All right. We now have an extra information. So, we do not want to waste any of the efforts that we have put in already computing an interpolating polynomial that interpolates at n plus 1 discrete points. But some little effort that we need to give so that we get now a polynomial of degree at most n plus 1 that interpolates at a set of n plus 2 points now. Using this extra information at xn plus 1 f of xn plus 1, the procedure is very simple in the sense that I require now a polynomial of degree n plus 1, right, and that is going to be the polynomial of degree n that I have already computed plus another term must be added to it, so that it is a n plus 1 multiplied by x minus x naught into x minus x1 etc. up to x minus xn. So, you observe that there are n plus 1 such factors, and so this term is a polynomial of degree n plus 1. Now, I would like to see what happens to this polynomial at the points I is equal to 0, 1, 2, 3 up to n, and I observe that it is equal to Pn of xi, and because when I is equal to n, this term xn minus xn will be 0. If I is 0, x naught minus x naught will be 0. So, at all these points the contribution from this term will be 0. So, we essentially have Pn plus 1 at xi is Pn of xi, but that is an interpolating polynomial interpolating the function f of x at points xi for I is equal to 0 to n. So, Pn plus 1 will satisfy the condition that at all the xi from 0 to n, Pn plus 1 of xi is f of xi. So, now let us see what will be Pn plus 1 at xn plus 1 at which the additional information is given. It is given that it must be equal to f of xn plus 1, and so that must be equal to Pn evaluated at xn plus 1, which can be done, plus an plus 1 into xn plus 1 minus x naught etc. up to xn plus 1 minus xn. So, from here we can determine an plus 1, and we know from what we have already done, we will end up with an plus 1 to be the divided difference of order n plus 1, namely it will be f of x naught, x1, x2 etc. up to xn plus 1, which we can compute. So, the an plus 1 is known, we can feed it here and arrive at the interpolating polynomial of of degree at most n plus 1 that interpolates the function at a set of n plus 2 points. So, given the additional information about the function, we do not have to waste our efforts which we have already put in to construct a polynomial of lower degree, use it and add another term that incorporates this additional information given about the function f, and that term will give you a polynomial of the next degree, finally ending up with the interpolating polynomial of the required degree that interpolates the function at a set of n plus 2 points. That is the greatest advantage of divided differences method, and the amount of calculations that are needed to construct the divided difference table is very much reduced as compared to the construction of Lagrange interpolation polynomial. So, why do you say that divided difference method scores over Lagrange interpolation polynomial? The reason is this: in case you have already computed Pn of x using Lagrange interpolation polynomial, say given the information at the first set of n plus n points, then what is it? It is nothing but k is equal to 0 to n Lk of x into f of xk, where Lk of x can be written down. Now you are given information, say at xn plus 1, and the information is f of xn plus 1. This is an additional information, right? The question is, can you do something like what you have done in the case of divided difference table? No, it is not possible, because for example, in constructing Pn of x, what was your L naught of x? It was x minus x1 into x minus x2, etc., x minus xn divided by x naught minus x1 into x naught minus x2, etc., up to x naught minus xn. But if you want to construct a polynomial of degree now n plus 1 to incorporate this additional information, the new L naught of x must be x minus x1 into x minus x2, etc., up to x minus xn into x minus xn plus 1 divided by x naught minus x1, etc., x naught minus xn into x naught minus xn plus 1. So, this must be multiplied by f of x naught to give you the first term. Similarly, each of those polynomials Lk of x and the Pn plus 1 of x now will be sigma k is equal to 0 to n plus 1 Lk of x into f of xk. So, each of these polynomials Lk of x for k equal to 0 to n plus 1 will have in both the numerator and the denominator extra factor that comes because of the information at xn plus 1 comma f of xn plus 1, and therefore the previous calculations or the efforts that we have put in to construct a polynomial of degree n that interpolates the function at a set of n plus 1 points will not be of any help to us in getting a polynomial of degree n plus 1. And therefore, the calculations have to be performed once again to construct this polynomial of degree n plus 1 when an additional information is given about the function. Whereas this did not happen in the case of the divided difference formula. The polynomial that we already have obtained is going to be used, and we just add an extra term that takes into account the information that is provided to us at this extra point, and that is why the divided difference method scores over Lagrange interpolation method. So, now that we know the definition of what the divided differences are, how to construct divided difference table, and what is the interpolating polynomial that is based on divided differences, let us take a simple example and then construct an interpolating polynomial based on divided differences. Okay, let us find the interpolating polynomial. Find the interpolating polynomial using divided differences. So, the information is given at x and the corresponding f values, say 0, 1, 2 and 4, and the corresponding values are 1, 1, 2 and 5. I am just illustrating the procedure. So, taking some simple example where information at 4 distinct points are given. So, the first thing that we should look at is, are the x values equally spaced? No, they are not equally spaced. So, in order to get an interpolating polynomial, I can use either Lagrange interpolation polynomial or divided difference interpolation polynomial. So, now that we have learnt divided differences, let us use the divided differences, and that is what the question is. So, we shall obtain the divided difference table and then construct that polynomial. So, I form the divided differences of order 0. So, what is it? This is our x naught, this is x1. So, this is our 0th order divided difference x naught, this is the 0th order divided difference f at x1. So, the divided differences of order 1 can be constructed by this minus this. So, 1 minus 1 divided by x1 minus x naught, so 0. Then 2 minus 1 by 2 minus 1, then 5 minus 2 by 4 minus 2. So, these are the divided differences of order 1, and we know that this by notation is f of x naught x1. So, now I compute second order divided differences. So, this is by notation f of x1 x2. So, how do you compute the second order difference? The difference between the successive first order differences, so 1 minus 0 divided by x2 minus x naught, this is x2 and that is x naught. So, 2 minus 0, so it is half, and then 3 by 2 minus 1 divided by x2 minus x1, so 4 minus 1. So, it is going to be half by 3, so 1 by 6. How do you denote this? This is f of x naught, x1, x2, and this is f of x1, x2, x3. These are the second order differences. So, we form the third order divided difference. So, that is going to be by definition 1 by 6 minus half divided by x3 minus x naught. So, it is 4 minus 0, and the value is going to be minus 1 by 12. So, the third order, given information at 4 distinct points, the third order difference, divided difference is constant, and the divided differences of order beyond 3 will all be 0. And how do you denote this? This is f of x naught, x1, x2, x3. So, we use this information in seeking a polynomial of degree 3. So, the required polynomial P3 of x that approximates the function f of x is given by first term f of x naught, which is 1, plus f of x naught x1 0 into x minus x naught, plus f of x naught x1 x2 half into x minus x naught into x minus x1, plus f of x naught x1 x2 x3. So, minus 1 by 12 into x minus x naught into x minus x1 into x minus x2. So, the polynomial is 1 plus half into x minus x naught is 0 into x minus x1 is 1 minus 1 by 12 into x minus x naught 0, x1 is 1 and x2 is 2. So, you see that you have a third degree polynomial that approximates this function or reconstructs this function f of x in this interval between 0 and 4. So, if you simplify this, it turns out to be minus x cubed by 12 plus 3 x square by 4 minus 2 by 3x plus 1. So, this is the required interpolating polynomial of degree 3 that interpolates the function at a set of 4 distinct points. So, we now have understood how we can construct interpolating polynomials using divided differences. So, we shall now look at some important properties of these divided differences.